Hey,
That looks good.
Okay,
I've-
go.
I think it's time to go on the air a little late, but better than never. And whoa, it's Labor Day 2022, everybody. Hot enough for you? It's our South Coast Telescope Club's weekly vlog podcast now underway. It's the SBAU Astro Hour, streaming on YouTube for members of the Santa Barbara Astronomical Unit, as well as astrophysics fans anywhere who stuck with us and got on YouTube in time here. This is the 5th of September edition, number 80, episode 80 of the shows we've done since March 1st of 2021 through the 11th, 5 to 11 September. We're live in our man caves, in our computer dens on Zoom, and we're on YouTube. And since Monday, March 21st, 2021, listen, ladies and gentlemen, the 80th version is going to cover, with yours truly, Ron Heron, in charge here, your vice president. Going to introduce you to the guys here in a minute. NASA's Artemis 1, ever going to fly? We'll talk about it briefly. The planets, the ones we can see in the night sky, some more sources of light out there again, the Zodiacal light, exploding stars in binaries, becoming, well, nebulas are us all over the place, and all about ion propulsion this hour. Let's meet the gang. President Jerry Wilson running the show.
Hello.
Learning the hard way. President, we got us on. Thank you very much. Amazing. His wife is Pat Forgy. It's been fourth season now. Chuck McPartland in front of the Ukrainian flag is our incredible outreach coordinator. His wife is our merchandise manager, wife Pat. We have another Tom. We have both Toms on today. Tom Whittemore, who's married to Maureen. Sobs every night because he misses his old job as science instructor out at Westmont, but that's all right. He's baking bread. Editor of our newsletter. Thank you for joining us.
Thank you.
We missed you two guys, you last two, Chuck and Tom, last week.
Right.
This is heading toward the fall equinox, isn't it? And now Tom Totten, webmaster, general, technical wizard, former president, and his wife is Suzanne, an artiste. Gentlemen,
So
welcome
let
aboard.
me just interject something here.
Okay.
When I was vice president, I found this cleaning up my office. So I got this in 2016, when I transitioned from vice president to president. So I've been president since 2017. So
It's been that's
It's
5
longer than it feels longer, but it is longer. We're always guessing, and I didn't remember.
What is that? What did you just hold up? What
An
was it?
award.
It's a little award for donating your time to the club.
Right. I have one for being a newsletter guy.
Yeah,
Really fantastic. Well, you deserve it. So that
you
means I
will get
guess
one too when your time comes.
Adrian Lopez, the former vice president, left 4 years ago for Caltech,
Yeah,
and he's being joined by one of the two lovely ladies who gave us an awesome grand tour on Friday
now
night.
Adrian has betrayed us. He's gone off into plasma physics, not into
or particle physics.
Particle physics, you're right, that's right.
Well, maybe that'll be what our next speaker is going to be talking about. Claudio Campagnari has, I think he's out at the physics department. I'm sure he is at UCSB. Is going to talk to us October 7th about CERN, C-E-R-N. I don't know what it stands for, but it's a particle accelerator thing. Meantime, let's start with some light stuff. We certainly need it in this heat, with President Jerry calling up just a few of the silly science cartoons that he forwards to us. And I've seen a couple that I forgot about, but here we go. Back to, look at this. What could possibly go wrong? There's a nuclear power plant. Oh, and a spider farm. What the hell is a spider farm?
Couple of really hokey movies. based on this.
There's a breakout, a mass escape, and here are two old guys that are very, very lucky. They're kidding. Are you kidding? I was struck twice by lightning as well as you, and here comes an asteroid to get him.
Some people have all the luck.
So if you don't have any luck at all, that's whatever. So there you go. And then one small rover it's a rover with attitude, and this is a good one. NASA's Mars lander has radioed back to Earth as it lands and begins its duties. One small rock for man, one giant waste of time for robot kind. While back at the JPL Command Center, the NASA technician on duty says to the mission director, he does this with every rock. And the robot rover radios back, Houston, you are my problem. You probably apply that to Artemis 1 in a way, because anybody know what's going on? What was it leaking yesterday?
Hydrogen fuel. It was
Okay.
a link to the spacecraft from the umbilical cord from the tower for fueling, I think.
So this giant monster was going to run on the same stuff that some cars run on, isn't it?
Oh, no, well, yeah, there are some cars that run on hydrogen. A lot of them don't run on hydrogen the way they run on gas. They run on hydrogen fuel cells.
Okay. But I was under the impression that in those two white candlesticks that used to power the shuttle into orbit, it was aluminum, actual fragmented or pulverized.
That's just in the boosters, yeah. But the main engines were hydrogen and oxygen.
Yeah.
Boy, that's sure different.
The aluminum in the solid is powdered aluminum.
Aluminum?
That's one of the components. There's other components.
Okay, gotcha. But it's hard to imagine something metallic that's flammable, because every time I've tried to light iron or steel or chrome, it doesn't burn.
It will if
Well,
you powder
you know what?
it.
You should take a Brillo pad or something that's like shredded steel, and get yourself an old 9-volt transistor battery and stick it into it, and you'll get a fire.
I've seen that on survival shows. That's how they start their campfires, right?
Anything as a fine powder, almost anything is flammable. It's a problem in the Midwest where they store silage. You know, the powdered wheat and stuff, the ground wheat, it can explode.
So the hydrogen is in the main unit, that big, tall giant they're going to sacrifice and not get back, like Elon used.
Yes.
With SpaceX, right? That's the hydrogen leak. Okay.
Yeah.
Anything else to say about Artemis before we go to the night sky with Tom Whittemore, who actually goes out and checks it out before dawn, better than night, or more often in the morning than in the evening?
Yeah, I mean, you want to hear about it?
Yeah, sure. What do you want?
Mercury is still coasting along the western sky after sundown. It is tough to see. You will very likely need binoculars, but I got Mercury several times last week. Okay, it's getting awfully close to the sun. It's involved what's called inferior conjunction. So it's going in front of the sun from our perspective. Okay, that's evening sky. Okay, in the morning, I've pretty much lost Venus. And so Venus has been skirting across the eastern horizon. 6:15, somewhere in there, but now it's really getting caught by the glow, getting caught by the sun's glow. As far as Venus goes, whereas Mercury is going through inferior conjunction, Venus is going through superior conjunction. So it's on the other side of the sun from our point of view. Really tough to see. Last week, I saw Venus several times with my bare eyes. Okay, but now it's really getting cast in the glow. I think its trajectory now is basically almost horizontal. Okay, so it's suffering from that glow of the sun. If you have a 0-degree horizon, you can try. We don't quite have that, but I have not had much luck in the last several mornings to see it. Again, I'm talking around 6:15 in the morning when I used to see it. Okay.
Well, according to President Jerry's talking points, it's near a star, Regulus. Do you know your stars there?
Yeah.
Regulus?
Yeah. So right now the sun is buried in Leo. Okay. And so when the sun goes down in the evening, it's kind of at the tailbone. Or you can actually see you really can't see it, but there is a star in the sickle called Algieba or Gamma Leonis. It's a really beautiful gold double. That is getting really tough to see. The sun is kind of embedded right in the center of the beast, but coming up in the morning is basically at the bottom of the sickle, which would be Regulus, the star Regulus. Okay.
So,
Unfortunately, I didn't include Venus and Mercury in the finder charts because they're so hard to see.
Oh, yeah. They're hard to see, Jerry.
Yeah.
They're really tough. Yeah.
Tom, can I ask a question?
Go ahead.
Sure.
The question is that can you see that golden double in Leo with binoculars or naked eye? Or
Oh, no, they're pretty close. I used to use Algieba or Gamma Leonis as a test double for when I was fashioning mirrors. Okay, and it definitely is telescope. And if my telescope mirror was getting pretty good, you could split them pretty easily. I forget exactly how far apart. Maybe Chuck knows.
I don't know the separation, but they are moderately tough.
Yeah, I would say 3 arc seconds to 5 arc
Which
seconds.
star is this you're talking about?
Now we're talking
Algieba.
about Gamma Leonis, Jerry, also
Okay.
known as Algieba, Algieba. It's that top pretty golden star at the top of the sickle.
Mhm.
By the way,
Where-
Tim
where-
Crawford is following along, and he says hi to everybody.
Oh, hi, Tim.
So that's
You
it
can
for
join us.
evening planet and morning planet. Okay. And then Chuck and you guys can talk more about the planets you've been showing at the outreaches. Okay.
Jupiter and Saturn and their
Yep.
moons.
I will just mention Mars, if you guys don't mind. Mars comes up from our perspective about 12:15 in the morning, and it drags along Aldebaran. So it's really kind of pretty. You see these 2 red things coming up in the east, okay, to the north of east, okay. And they are separated, to my point of view, by about the same distance, angular distance as is Castor and Pollux in
Mhm.
Gemini. And those stars are coming up around 3:30. I see those, and those are further to the north, coming up in the northeast.
This shows the configuration of
Oh,
Uranus
okay, thanks.
and Mars at 2 a.m. during
Okay.
this week.
Mhm.
Well, now, Jerry, you enlarged that so much that you got rid of that bright glowing ball on the lower right. What was that?
That was the moon.
Oh,
The fighting moon is, oh, that's a to come yet. The moon is just a little past first quarter right now, and it's heading toward full moon by late this week.
okay.
So it's not interfering so much with the Mars and Uranus, which come up, or rather are high up at 2 o'clock. But it did show up here on this chart for
Yeah.
Jupiter and
And Saturn.
Saturn.
Saturn. Mhm.
Yeah. So
It-
Neptune.
Oh, I just,
and
it's a really pretty combo of 2 beautiful red objects, Mars and
Jupiter. And over here is, well,
Saturn, you went past. It's
Pluto.
in the left side of Capricornus there.
Yep.
Well, Tom,
Saturn's up, when the sun goes down, pretty much, right, Chuck?
Yeah.
Tom mentioned something I think that you mentioned in your talking points that I hadn't heard of. Sickle of Leo. That's another asterism as part of the Leo.
Yeah, the sickle. Yeah, it looks like a.
Oh, yeah, there it is.
question mark.
down here, Saturn.
That's shaped like a sickle.
Mhm. That's the head of the lion, Ron.
Yeah,
Oh, it's okay. And it's another asterism. Boy, I'm learning all about
but
asterisms.
you can't see that at night. It's setting as the
Yes.
night starts. So this is not the right season for looking at Leo. That would be like the springtime, like March or April.
Right.
Ah.
Mhm.
And
Yeah, I
Venus-
think of Leo the lion as a spring.
Yeah.
Mhm.
Well, it's got all those nice galaxies in it. And we're looking out of the North Pole of the galaxy in the springtime, about that February, March, April.
Right. And I guess Tom Whittemore is the only one actually going out and looking at them. Mr. McPartland is our oculator or oculation expert. Have you occulted or whatever the word? I'm not sure how that
He's
stands.
having technical difficulties right now with his scope for occultation.
Yeah.
Oh, that's right.
This shows the configuration at midnight on a typical night this week. And the moon position specifically on September 7, which is Wednesday night.
Mhm.
At midnight.
Are you saying it'll be full?
No, it's a
No, I
given
think-
phase. It doesn't show them phase real accurately here.
Yeah, I think it's full around Friday, Ron.
Yeah.
Well, then we're going to have an awesome star party next Saturday night.
Yeah.
Incidentally, everybody's invited to that. That's after our board meeting. And
Well, you can still see individual stars, double stars, and you can see brighter clusters.
Yeah. Well, the moon occupies only 1/700th of the complete 360 degrees around the Earth anyway, or around anything, right? Half a degree?
Yeah.
Yeah.
Got
Yeah,
it.
in the sky, it subtends a half of 1 degree, just like the sun.
Okay. Jerry, have your cat answer that phone.
So that's not at my place.
Oh, okay, that's all right.
My phone is a Tarzan yell.
You better turn it off, or
That way I don't mix it up with anyone else.
oh, I got you. Sure, right. Do you want to talk about the strange glows in the sky, or are we done with? Where has Venus gone? It hasn't. We've just had trouble finding. That was your
It's just really tough, Ron. It's really tough to get.
tough to see and hard.
Now, last week we talked about and fumbled the topics of
Zodiacal light.
zodiacal light. So I promised a expansive in context view of that this time.
Okay, well, it's not what we're looking at. It's not the side view of the galaxy itself, is it?
Well, this is the side view of the galaxy.
Right.
This is the zodiacal light,
Huh.
and this is the Gegenschein.
Okay, that was a new word.
So this is near the horizon. This is opposite the sun for us.
Oh. How about
From
airglow?
From the German, Ron, for against. Gegen is against.
It's similar or a totally different phenomenon?
Well, this represents the ecliptic, and this is just the random dust that is orbiting our sun in a disk. And so at low angles, the sun bounces off this dust, and you see it as a zodiacal light, not every time of the year, but sometimes, depending on the orientation of the Earth's tilt. And then this is something that's very faint and difficult to see. You usually see these things interrupting very dark skies. So this is right opposite the sun.
We were seeing that at Refugio last week.
Wow.
Oh, you did?
Yeah, it was a really nice sky. Not so much the Gegenschein, but we were seeing the zodiacal light as a strange little band of light.
It's pretty cool.
Yeah, going across the sky. And they were having some kind of TV show production at Dos Pueblos Ranch. So when we were driving home at midnight, they had spotlights just weaving all over the sky.
Wow. Yeah, I was going to mention something, Chuck. This is a really neat shot that Jerry picked up, because basically the Gegenschein and the zodiacal light are in the plane of our solar system, right? The ecliptic. And then you see how the galaxy's plane is inclined by about 60 degrees to that plane. That's really cool, Jerry, what you pulled in.
Well, what's that bright light on the extreme left?
That's a star. Or
It's a
the
star.
star or something.
Or Jupiter or Venus.
Yeah.
Yeah, and in the middle of this, of course, you're looking down into, the tailbone of Scorpius and stuff. But what you see there is the Pipe Nebula, very, very prominent.
Right in the middle.
Yeah, right in the middle. Some people, at least I do, I see it as a little galloping horse, but I learned it to be a pipe when I used to be in the San Jose group up in the Bay Area.
Huh.
In Australia, a lot of the indigenous quote constellations, they actually make constellations out of these dark patches in the Milky Way because they can see them so well.
Because they could
Because
see
they're blessed with, great dark skies.
So what is it about the zodiacal light that you can see it more in the spring or the autumn? Why is that?
The plane, the angle of the ecliptic relative to the horizon, when it's very orthogonal to the horizon, it's easier to see.
Right, that's it. Nailed it.
Well, what about airglow?
That's everywhere.
This is another picture of the Gegenschein,
Wow.
Okay.
and this is zodiacal light.
Oh, this is airglow.
Oh, airglow. Is it airglow? Did I?
Yeah.
You're right. That's airglow. I've learned them in order here. Yeah. You're right. Airglow.
This is what you wrote, sir. Comes from atoms high in our atmosphere that have been photoionized by the sun during the daytime. Luminescence.
Yeah. They're relaxing at night. Oh, day is over.
Wow. So you're ready for Baron's dumb question of the day, of the week? The side view of the galaxy will always be at that angle for now, or as we slowly go around the galaxy. Does it ever change, you suppose? Does our flat ecliptic ever turn, or are we like a gyroscope that's
that could generate a very complicated answer.
Yeah.
As our sun goes around the galaxy, dragging us all in the solar system, it takes about 240 million years to go around once.
right?
The sun also wobbles, and it basically cranks us. And I'm talking about the solar system,
Yeah.
up and down and up and down and up and down. So there's a wobble there. So that's a complicated answer, Ron, to your question. It probably does. Yeah. But that's about all I can say about it. I forget the frequency. Maybe Chuck or Jerry or Tom knows.
No, but it's a definite sine wave up and down relative to the disk.
That is right. That is right.
Not something you're going to worry about on a human lifetime scale.
That's right. Yeah.
So would it be safe to say we're turned to about a 60-degree angle to this?
Yeah.
Yeah.
So that is for sure, Ron.
Okay.
So the plane of the solar system is inclined at 60 degrees with respect to the central plane of the galaxy itself. And you can see that in this picture. It's just an amazing picture.
Sure.
And that's the angle to the left of the center there. You see that?
Yeah,
Right in there. Yeah.
right. Yeah.
60 degrees.
This is the Rho Ophiuchi area in Sagittarius. Not Sagittarius, Scorpius.
Mhm.
And Ophiuchus, obviously.
Yeah.
Right. Chuck's sign.
Yep.
Now, where is the running horse? I don't see that.
Oh, it's right in the middle, Jerry. So I learned it as the pipe, like a pipe throwing smoke out.
Maybe if
Are you
you
talking about these dark areas or this dark area?
Yes. All of the above, right
Oh.
there in the middle.
Okay.
Yeah.
maybe if you enlarged it, Jerry, we could see it.
Yeah, the
So
very
it's like-
darkest part in the middle is what I think of the pipe nebula, and here it's sort of upside down.
That's right. Yeah. This is probably taken in the southern hemisphere, huh?
So
Yeah,
That overhead, yeah.
Yeah, Scorpius.
Yeah, because it's so crystalline, it must be way overhead.
Yeah.
So this is another horse other than Pegasus, which is a total different animal.
Well, Ron, that's just how I see it. I always looked at it as a galloping horse. I'm probably unique, so.
Well, we'll name it the Whittemore horse asterism.
Which
Yeah.
way is the horse facing?
Kinds of towards us, I think.
Yeah.
Oh, toward us?
Yeah.
Yeah.
If you
Right.
kind of take the stem off the pipe and just look at the pipe part in that very darkest part in the center,
Yeah.
sort of see the horse's head is up and his legs are coming down, but they're dimming down a little bit, and then his rear end is receding into the distance.
Yeah. I would say, Jerry, the stem of the pipe is running left-right there, the darkest thing you can see. Yeah, right
Yeah.
there.
So this one hasn't generated politicians yet.
No, that's Pegasus or
Okay.
Taurus.
Yeah, we need to
I
turn
guess I'll
the
have to look at that some more. I don't get a horse out of it.
web.
Okay.
Okay.
Maybe the Webb will look at it, the Webb telescope.
Jerry, can
Sure.
I show something on the screen about
Yeah.
the galaxy angle?
You-
The angle of the galaxy versus the solar system. There's some good images on.
Oh,
for
yeah,
this-
go ahead.
let's see if-
Great. Thanks, Tom.
Oh, host is disabled, participant screen sharing. Oh, maybe I can't. Maybe we've got that turned off on our Zoom meeting somehow. It says host disabled, participant screen sharing. So guess I can't do that. I'll have to look at
Wait a
the
minute.
settings that we have on Zoom. Somehow the participant screen sharing is not
Try it
available.
now.
Okay.
Try it now. Share screen. Oh yeah, there we go. So turn it back on. Let's see. I think this is it here. You see this image here? Let's see if we can make it
Yeah.
bigger.
Okay.
Yeah.
Ah,
Is-
And
Yeah,
there you
there
can
it
see
is.
that
There-
oscillation.
I'll be damned.
And you get that long-term oscillation too, yeah.
But when it goes up and down, does the tilt change? Yeah, I think that the up and down is more like a horse on a carousel.
Yeah.
It doesn't.
Yes, yeah.
You're kidding.
I forget the periodicity of that, Jerry. Chuck, is it longer than the 240 million journey
No,
around?
no,
No,
I think there are
it's-
multiple waves in there.
Yeah,
Okay, it's more frequent then. Okay.
I had the impression there were somewhere between 5 and 10 waves like that going around.
Okay.
There we go. Nice.
But can you imagine the problems we'd have or the confusion if our sun's ecliptic was on the same ecliptic, the same level as the platter of the galaxy? And all we saw on the horizon was brightness. And
That's what it's like in May.
Well,
Right.
we would see it from here as brightness if we were kept right but on the horizon, but someone else on the Earth would see it overhead.
Mhm.
Yeah.
well, you
I
probably
mean,
wouldn't
the
see
Milky
any-
Way can go around the horizon in May, but the ecliptic is always going to be low or high depending on where we are in the seasons.
Right. And to me, that makes the year very interesting and fun.
Yeah.
That things do change. Yeah.
Is that the Earth we're looking at, Tom Totten?
No,
Yeah,
that's
Oh, no.
Showing the different, the celestial equator, which is the
Hmm.
north off of the Earth's equator, celestial equator. So that'd be the equator of the Earth, right? And then
Yep.
the ecliptic is
Yep.
the path of the tilt that we have, causing the planets and sun going across the sky. And the galaxy's got its own equator.
I got you.
And you see that 60-degree angle, Ron? See that piped in there? There it is.
Wow. But otherwise, all the different stellar systems have different angles. We're not all the same lined up like ferrous atoms of iron in a magnetic field.
Right. Right.
Yeah.
Although there are some weird orientations people have noticed in some of the rotational axes. I think they mainly get it from the axes of planetary nebulae.
Oh,
Mhm.
wow. Fascinating stuff. Amazing.
All right, I'll stop sharing that.
Well,
That's good. Thanks, Tom. That's good.
great stuff. I floored one of my friends with a question I brought up before. High in the sky in the summer is the sun,
yeah.
and low in the sky in the winter is the sun. How about the full moon during those times?
Full moon is opposite the full sun.
It's just, right. It's opposite that.
Well, nobody I present that problem to can get it, and I had difficulty explaining why. It has to do with where we go, I guess, when we go into the night side, right? We're not in the sun's direct, never mind.
You're looking at the opposite point in the sky from the sun.
Exactly. Exactly.
There you go. That's
So
it.
when the sun is
Yeah,
low, the
get
moon
full
is high.
moon. Don't forget, Ron, to get a full moon, you have to have the moon opposite,
Yeah.
from our perspective.
That's true, but I was talking about our seasons and the 23, is it
Mhm.
23 or 27 degrees the Earth's tilted?
23 and a half.
23 and a half. What are we looking at here, Mr. President?
We have switched topics now to the shapes of planetary nebulas.
Aha,
We showed you last week, we discussed, I believe it was M57, and you were not convinced that it was not a sphere. These things are seldom spherical, and you can read the text for why. But also the Helix Nebula, which is a fairly faint planetary nebula, and looks very similar to the M57, the Ring Nebula. But the Helix Nebula is called the Helix Nebula because the nebula is actually in the shape of a spring, and we're looking lengthwise down the spring, but it looks like a ring because of our perspective. This one, I forget the name of it, but you can look on the caption and see. This one is also not a spherical shape, but we're looking down a axis of symmetry for it. So it gives it a roughly round shape, but there's all sorts of more complex things happening in here. And this one is looking sideways at one. This is the Butterfly Nebula. But if it were one of these long axes were pointed at Earth, we would see this just like this.
oh,
So they're oriented all over the place, and we get a favored perspective, so to speak.
and it's all the follow-up of a supernova.
No.
No,
It's a star.
there's no nova or explosion involved. This is just a burp that sheds outer layers, and it doesn't do it all at once either, like a nova. it will all of a sudden get a super solar wind and just stream things out. It will, and it streams them out, even though the star is spherical, as the talking points point out. It depends largely on the environment of the star, how the eventual distribution of gas looks from far away.
Well, here's what your talking points said. What decides the shape of a planetary nebula? Answer, whatever's orbiting the star when it dies.
That's right.
Or a strong magnetic field.
Yeah.
So we're the center of it, that white star in the middle, is it the one that's orbiting the other and the other is gone, or is that the main?
No, it could be that star and planets around it, like a Jupiter planet.
Oh.
It could be a double star too, but that's in the middle, so it's likely the planet of the star that shed this gas.
Okay, well, some parts of that gas are, and in this one too, are lighter than others. Why is that? Just concentration of heat and.
Yes, these things are bright because they get unedited view from the sun. These other ones are darker because they're emitting the light and they're shaded from the bright direct sunlight, starlight.
But now to form a butterfly shape like that is rare, or do they all do this?
It's
Depends on
common.
their angle seeing it.
Huh.
Huh.
To get an actual spherical shape, it does happen, but that's the rarity.
The spherical is the rarity.
Yeah, the nice spherical bubble is the rarity.
So
Even the bubble nebula is not bubular.
Yeah.
but this connotes to me that it blasts in two directions on opposite sides of itself.
Yes.
Primarily.
And the orbiting object that's channeling the flow is perpendicular to that, near the center.
Oh, okay.
It looks to me, and this is purely a guess, I haven't read anything on it, but it looks to me like this hourglass shape is girdled by a dark cloud.
Mm-hmm.
And so this star may have shed its outer layers while it had this very dense gaseous cloud orbiting it. And so the only way it could freely come out is at the poles, because it would just run into this gas cloud as it came out along the equator. And it might be rotating very sharply, and that causes it to focus on the poles.
And so it's not a supernova.
No. Not a supernova, not a nova, not an explosion.
This is a planetary nebula like our sun will do, like the ring and like the dumbbell.
Okay, but it says in his notes that when the star dies. what does
Yeah.
that mean?
Our sun is not going to explode.
Oh.
It's not massive enough.
It'll expand. It'll become a red giant, won't it?
Yep.
Before this, yeah.
Well, most of these do that too. They go red on us. Betelgeuse will end up like this soon, right?
No. No, Betelgeuse will blow up in a core collapse supernova.
Oh,
Oh, Jerry, can I show a Hertzsprung-Russell diagram that shows the kind of the sequence of events for going to a white dwarf?
yeah, that's
Okay,
great.
go ahead.
Okay, see if I can find it here.
Hertzsprung-Russell diagram connects the temperature and the luminosities of stars.
Very good. So you can see this is for a five solar mass star, and they're showing the star on the main sequence, luminosity, and then it somehow, I don't know how quickly this happens, jumps over to be a red giant. After it runs out of burning hydrogen and helium, if helium starts burning and the star blows up into a red giant. And then here they're calling something called a blue loop, which I'm not sure. I guess it goes to the blue color, gets hot first for a bit. Let's see. When helium is exhausted in its core, the star.
Color. This is the color axis up here. Can you see my cursor?
Yeah.
No, just have mine.
Yeah, up on top, those surface temperatures define color. Our sun is yellow, so it's about 5,000. Something up at about 8,000 would be whitish, and up in that, over 10,000 would be blue.
Yeah, okay. So that the colors on this chart correspond to the colors of the
Oh,
star.
yeah, they do, yeah.
And this is
Right.
for a 5 solar mass star. So this is,
Bigger than our sun.
yeah,
But still not nova.
right.
And
Not
then- and then-
supernova. Yeah.
and then so it goes to some other branch here. So when helium is exhausted, it does this asymptotic branch, giant branch, whatever that is. For how long, I don't know. And then here at the very end, it shoots over and becomes a hot 100,000 degree white dwarf for some time.
Yeah.
Okay, so there's something left in the middle of those nebulae, and those are usually white dwarfs.
Yes,
Yes.
it's a star that's no longer burning anything, and it's just cooling off.
But it's real hot because it's the core of a hot star.
Right.
Huh.
Compression makes things hot. It's how diesel engines ignite their fuel. When a star loses its outer layer and suddenly collapses, what's down in the middle gets very hot due to gravitational friction as it collapses.
But then how do you define supernova, hypernova, kilonova? Those are all
Well, those are much more energetic. A
okay.
supernova is where you get an explosion, and there are several types, but the type we're considering is a core collapse supernova where the star makes iron in its core and then explodes. You can
Yeah.
also have ones where white dwarf stars collide with each other and exceed a certain mass, and then you get a blast, and that's a type 1 supernova. And then a hypernova is where you get really, really, really energetic explosions, which may be from collisions of very massive stars, or it can be magnetars blowing up.
Magnetars.
And you get these gamma ray bursts.
Yeah.
And kilonova is a collision of neutron stars.
Oh my God. Well, is a white dwarf the last step before black hole?
No.
It
No.
is. What's next? Neutron stars. Can they go through stages?
Okay, so Ron, when you get a core collapse supernova, the leftover can be a neutron star, or if enough mass falls back down on the debris, the neutron star winks out into a black hole. So they're the result of some kind of supernova. It could also be something called a pair instability supernova. There's all kinds, okay? But a white dwarf is basically the core of your star. And like Jerry said, it's not fusing any elements anymore. It's just radiating away whatever heat it has from its lifetime and its collapse. And eventually, and there hasn't been enough time yet in the universe for this to happen, eventually the white dwarf will radiate away all that heat and become a black dwarf, which is basically a cinder. It could be even charcoal because of carbon is one of the elements that may be left over from these low mass stars.
But none of those definitions you just described apply to what we're looking at here, the nebulas?
Yes. This is where there's a white dwarf left at the core.
Okay, but you don't get a nebula from a neutron star or from a black hole or.
Well, you get yes, you do. The Crab Nebula is a supernova remnant, and left over in the core of that is a neutron star.
Unfortunately, the Crab Nebula looks like a planetary nebula because of its size, a trap I have fallen into a couple times, but it's not due to this process.
It doesn't look very organized. It's a modeled mess, isn't it? That Crab Nebula.
Yeah.
Yeah.
But you can get things like the Veil Nebula, where if you take all the parts together, you got a spherical structure, or a circular, at least it looks from our point of view.
And you can also get like the Gum Nebula in the southern hemisphere.
But can we see white dwarfs? Are they only?
Yeah.
Sure. Right at the core of M57, the Ring Nebula, we can see the white dwarf. It's a 14th magnitude star. So you could see it probably in Chuck's 11-inch.
Yeah.
9-inch.
I've seen my 18.
Yeah.
Okay.
But due to the collapse, a lot of them are only the size of the Earth, aren't they?
Neutron stars.
Oh, okay. That's
Oh no, white
sorry.
dwarfs are yeah.
White dwarfs
Size
are
of the
Earth size. Neutron stars are city size.
oh my God. And what's a magnetar? That sounds frightening.
That's a neutron star that's really heavily magnetized.
Wonder why.
High spin. Something's charged and it's going around at a high rate.
Not
So
overwhelmed.
it produces a current, a circular current.
So Chuck, Tim is saying, do black dwarfs just eventually fade away?
Yeah, white dwarfs eventually fade away into these black dwarfs, but there hasn't been enough time yet in the universe for one of those to do it.
Mhm.
Black dwarf, is that the next step to black hole?
No,
No, no, oh, no.
What black? The girl that talked to us this Friday is a specialist in brown dwarfs. That's totally different animals. That's a planet.
yes.
Yes, that's a star that didn't quite make it.
Okay. Interesting, fascinating stuff. We got 15 minutes. You want to talk about ion engines?
Briefly,
Yeah, this is good stuff. Fascinating. That I didn't know they were doing it already, but apparently ion thrusters are up there. Ion drive, ion engine. Ions are us.
yeah.
Yes, go ahead.
Ion engines have a lot of advantages. These are different types of ion engines. Those I didn't mean to show. This one I didn't mean to show. I gotta edit this more. This is the Kepler. Is this the Kepler one?
Kepler spacecraft, yeah.
Yeah. So this is, and it it has an ion engine in it. Or no, it doesn't have an ion engine in it. It was using rockets, hydrazine, and it ran out of fuel. And so it's basically useless up there. If it had ion engines on it, it would still have a long lifetime ahead of it because they are very efficient at fuel and they give better performance than the rocket engine does.
Really?
So this is,
That's an ion engine right there.
This looks
Yeah.
like Dawn.
yeah, this is the Dawn spacecraft. And as you recall, the Dawn spacecraft went out and orbited Vesta, the asteroid Vesta, for a while, and then it moved over and it orbited
Ceres.
thank you, and in a series of descending orbits. So this one uses ion engines for both propulsion and for attitude control. You can see other ion engines around here for attitude control for pointing. So they have been under development since the 60s. When I first started briefly with Hughes Aircraft Company's Malibu Research, what was it called?
Malibu Research Facility, I think.
Yeah, but there was another name, Hughes Research, HRL, Hughes Research Labs. They were starting on doing ion engines for spacecraft. They didn't perform very well then, but they had a lot of potential. The physics was really good on them. So they've been developed now to where they have a number of types of them that are being developed and used, being produced and used, and where a number of them, newer ones with bigger thrust, are being developed. The bigger ones are being developed to the point where they're being considered for the main cargo delivery for, say, trips to Mars, for example. The way we do it now for Mars is we set off a rocket, a chemical rocket, like the Starship will be, or like the SLS will be, and we point in a parking orbit around Earth, and then the upper stage fires a chemical rocket and heads toward Mars, and it coasts all the way. You can get there more efficiently and easier, but longer time by, actually correct that, not longer time, by using an ion thruster. They're up to the level where they can push a payload now, although we don't have any of those in operation. Mostly they're for small satellites. This one is a gridded ion thruster, and this uses simple Coulomb energy. So it has two grids in it. A grid that they have an inert gas like xenon or argon. They strip an electron off of it, and there's a mesh out in front that is oppositely charged. The xenon with the electron missing is negative or positive, and the charge out, the plate out front is negative, and that attracts the positive ion, which rapidly gains energy. And the velocities that these ions come out at is just phenomenally high. As it leaves the spacecraft, once it's out, the electrons it took off of argon are sprayed back into the exhaust. So it neutralizes it, giving it a good environment to operate in. This one uses Coulomb force, The Hall thruster, there's two ways to get force out of it. One is to have the electric field aligned in the direction of the acceleration. The other is to have a magnetic field aligned perpendicular to the direction. And then you use the famous right-hand rule, which you all may remember. So you have a magnetic field this way. So that way you have a current this way. No, a current this way, and your resulting force is perpendicular to that, the famous cross product for the Lorentz force. So that's the Hall thruster. This is the magnetoplasma dynamic thruster, which uses the Lorentz force. This uses a Hall effect, which is again to have a magnetic field perpendicular to an electron current flow, and it changes the current flow to be out and react to that through Newton's third law. I don't feel that was a very good explanation, but anyway, that's the way it is. So a lot of these are used on current spacecraft. For example, this is a artist perception of Bepi Colombo, a collaborative spacecraft that uses ion propulsion for its main source of energy. Oops, and that's all of it. Now, the number of spacecraft that we have operating is probably in excess of 50 that have ion propulsion on board for the payload and for attitude control.
I think a lot of these mini sats that go up now also have really small versions of these ion thrusters.
Yeah.
You know, it's almost thrusters on a chip.
Now, this is not an ion thruster like you see on Star Trek, where you see the stars whipping by because you're on ion drive, but they do leave an ion trail that you can follow. So the key thing is not that it's a high thruster, but that you thrust for a long time at a low to medium thrust, and you build up tremendous speeds. They're much more efficient at getting to high speeds. The rocket motor, which gives you one giant boost at the front, and then you coast. So
the Wikipedia page says that SpaceX is using it for their Starlink satellites.
Yeah.
All those.
This is very long. I should have copied it down and set it up here. But let's see, what was the other point that there was? Oh, well, go ahead.
Can I ask this? Was it Newton that said for every action, there's an opposite and equal reaction? And
That's his third law of motion, yeah.
Okay. And the only way I can conceptualize how this would move something forward by simply ionizing and going out the back is that it sort of explodes in all directions, therefore pushing the spacecraft or the.
So that's a chemical rocket's explosion. This takes an ion, it makes an ion, so now it's charged, and it accelerates it by either attracting it in an electric field, that would be a Coulomb force, or by having a cross magnetic force, and that would be the Lorentz force, where it throws it out the back. It accelerates the ion to a very high speed, and the ion has mass, and it has an extremely high speed. So you would think of this as a very light material, but it comes out so fast that it gives a good acceleration to the object.
Ron, one way to think of this ion engine is like you're in a canoe and you have a bag of golf balls, all right? And you throw the golf balls toward the stern of the canoe, you know, away from you. And that will actually propel you in the forward direction.
Well, I don't see it propelling my canoe.
Yeah, it would. Because you get the equal and opposite reaction. You've given so much momentum to the golf ball, right? And that same force has been applied to the canoe, and it'll push it forward.
Okay. I read a science fiction story one time where a guy in a spacesuit took along a .45 automatic pistol as a safety emergency thruster, and no one understood what he was doing. But when he got stuck out in space, he pointed the pistol away from where he wanted to go and fired off a shot, and it propelled him in the opposite direction. So that was his get back to the spaceship when you're not attached. Fail-safe.
And he didn't need oxygen or air around him to light that bullet?
Like a rocket engine, the powder inside the bullet, inside the casing, has its own oxidizer in there.
It just seems to me what we're looking at, the little blue flames that are coming out, that's the only place they can go. They want to go everywhere, wouldn't they? That's not an explosion.
No, they don't want to go everywhere. They follow the electric field.
Oh, but it's
in an explosion, they go everywhere, and there's this big bell-shaped burning chamber, and then the molecules go out in every direction, but they can't get out of the engine without going out the back. But they heat everything up, and they just then get forced out the back because that's where the pressure is relieved. This is not like that.
Isn't it like shooting the bullet out that end and the rifle kicks back on your shoulder or the gun?
That's common to both of them. They both have an action and a reaction.
But these suckers will never be big enough and powerful enough to put an Artemis 1 or 2 in a.
No, they're headed that way. That's what I said about that. Is there are some in development that are capable of launching cargos,
but not yet of lifting the rocket out of our gravitation.
Yeah, they don't work in an atmosphere. They have to work only in space.
Oh,
there's too much air resistance. They don't have enough actual thrust to overcome air drag.
And so how do you basically describe what ionization is? Something's changing the atoms, they're adding electrons, or
removing electrons.
Something pulls an electron off the atom.
Okay, and that gives us the power somehow.
Yeah.
Well, that makes it charged, and then it reacts to the electric field.
Okay. Is the ozone layer a home for a bunch of ionized atoms?
There is an ionosphere over our Earth, but it's not the ozone layer.
Oh, it's a layer up there. Okay. Fascinating stuff, gentlemen. I think we're down to the wire, but we got about 2 minutes. We started late. We could still go 2 more minutes.
Oh, no, we recorded our antics trying to get on YouTube live. So we've got a full session, kind of an embarrassing lead in, but we got a full session.
So Tim is asking a question. It says, is there a limit where the ion thrusters can be used efficiently in gravitational fields like on a planet? I think you guys kind of answered that question by talking about it wouldn't make sense for trying to lift yourself off the Earth or whatever.
No,
well, maybe from a comet or something, some small object in space.
Very small, yeah. It's mostly for orbiting and changing direction in orbits. The lifting off a planet, it does not have enough thrust for that, even Mars. And the atmosphere would interact negatively with the ions.
And if you were using these, like when they were going to Ceres and Vesta, you accelerate for a while to get up to speed, but then as you're nearing the object and you want to go into orbit, now you have to decelerate. And so you have to really plan ahead with these ion engines, and you have to flip the spacecraft around and start firing it the other way to decelerate so that you can get captured into orbit.
Well, tell me this, if you were next to one of those blue, they look like flames, but let's just say expulsions we're looking at the bottom of the screen, would you get burned?
Oh, yes.
A lot of energy in those heavy nuclei.
They're very hot. Okay. Wow. So you'll never see one off a launch pad powered by these suckers in Cape Canaveral. That's fascinating. What is the space thing we're watching? What is this device, this satellite we're looking at? One of the
Bepi Colombo is a mission to go to Mercury, I believe.
Yeah.
Oh.
Currently, it's not there yet. Currently, it's orbiting. It's about as far as Venus, I think.
Ron, I thought that was a rock star on tour.
Yeah.
Bepi Colombo. No one's got to that name yet, but
I'm wondering what that round thing on the top is. Looks like a smokestack or a.
No, I think that's a sun shield on a camera lens.
Oh.
That'd be my guess.
I got you. Sure. Yeah, with Mercury.
These, of course, are solar cells.
Fascinating stuff. Bepi Colombo. I did see that name. I don't know what it means, but that's the name of the satellite, Bepi Colombo.
Yep.
Also a Saturday morning cartoon that I watch on PBS. Well, gentlemen, Tom Totten, so good of you to join us again. And you guys are working together, and we're going to get this hookup to YouTube down. I got to tell you, folks.
We got it down. I just didn't recognize something, but Tom told me what to do, but I just didn't recognize it.
Well, it'll work.
So.
I got nothing but confidence in you, and I'm still having fun, and we love sitting around even on a Labor Day, which doesn't celebrate us, does it? We're all retired.
So stay healthy and stay cool.
That's right.
Okay.
Stay as calm.
See you all.
Yeah.
Okay.
We'll do it.
Bye.